Good morning, everyone. Okay, the last day of this week. Excited? I think most of you maybe not because we have so many homework, lab thing you need to finish in this weekend. But uh, if you have any questions and a problem, and please email me. Even the weekend, I will like reply to you like when I see the email. Is that okay? Okay. Um, Today we will still focus on sound and light waves. And let me share my screen. Okay. Before we start today's class, I want you to like I will send you like a course invitation like a link for the pivot interaction like a website, and this we will finish the lab 2 in this website, and this is a specific like a website for the physics labs. So I will send the link to you guys, and you just need to enroll this classroom. And yeah, you don't need to pay. You don't need to buy the license because we have already paid that for you. So what you need is just enroll my class, and you will see the lab. Is that okay for you? Okay. Any question? Just let me know about that part about that website. Okay. Today we will still focus on the like sound and light waves. And okay, like I talked in last class, in chapter 50, we focus on traveling waves and like sound waves. Also, maybe I just missed one thing. That's fine. And the goal of this chapter is to learn the basic properties of traveling waves. Actually, we have already learned some in the chapter in next class, and today we will explore more. And before we talk about explore more, and let's talk about today's goal. And today's goal, and firstly, we will review the traveling wave we have already talked in last class. And then we will learn about sound and light waves. We will explore more about sound and light waves. And after that, we will understand the energy and intensity intensity in traveling waves. And then we will learn how loudness relates to sound intensity. And finally, we will explore the Doppler like effect and shock waves. Is this part is just similar like the applications? Yeah. Okay, let's review what we have already learned in last class. Yeah, in last class, firstly we talk about the wave model. Actually, the wave model is based on the idea of traveling wave, which is an organized disturbance traveling at a well-defined wave speed v. Yeah, the wave model, which means it's like a pattern thing. Am I right? So because although we talk about this in last class. Although there are so many different waves, like light waves, sound waves, and microwave, and yeah, many waves. Yeah, but string waves, yeah, but they have some they share some same things, same properties. Yeah, so this is the reason why we can get the wave model. Yeah, and for most waves, it can be fall into two different types. One is transverse waves, and the other is longitudinal waves. And the in transverse waves, and the particles of the medium move perpendicular to the direction in which the wave travels. Like we analyze in last class, and this is the wave travels direction, and this is practical of the medium move like you can see it's up down. This is like a point. For example, this point it will move up down up down up down. So this is a perpendicular, yeah, relationship. So those kind of wave we call it a transverse wave. And in a longitudinal wave, the particle of the medium move parallel to the direction in which the wave travels. And this is, yeah, you can see this is the wave travels. And this like a particle of the medium, it's just move from left to right, left to right. It's the same like direction, like with not same, it's parallel because you can see it will like move to this direction. It's parallel. So this kind of wave, we call it a longitudinal wave. Like a wave like remember like we talk about this, like a wave transfers energy. You can see in the beginning, like this string, this like a spring is still, yeah, it just still, it's just like a put it in like on the floor or put it in a desk like that. And then you give this string or like a spring a force. Yeah, like the up down force or like a right left force. And this like generate a wave like travel through this medium through this like a spring or like a string. But this is just a transfer the energy because when you give the give this string or like spring a force, which means it generates some, it you give me some this some energy, and then this energy will be transferred. But there is no material or substance transferred. Yeah, you can see this string, all this string is also that string, that spring. Am I right? This string will now become longer or shorter, and this spring also now become like a harder or softer. Yeah, that makes sense to you. Yeah, this is what we have already talked in last class, and also in the wave there are we talk about two different kind of waves, mechanical waves. The mechanical waves actually they require a material medium. For example, the spring wave, yeah, you can see this wave is transferred by through the spring and like string. The sound waves, yeah, like you can see if you speak to others in a vacuum like environment, the others will not hear you. Yeah, I think yeah, you heard about this, am I right? And also like the water wave, yeah, you can see the water wave only like transfer in the water, and like the spring wave and like stream wave, yeah. And the speed of the wave is a property of the medium. Now the wave, yeah, you can see the speed of the wave. We talk about this like just like related to a property in the medium. For example, for the like a string, it is just the tension and the like the identity. Yeah, yeah. So it's now related to the like a wave. Just related to the property of the medium, and the speed does not depend on the size or shape of the wave. Yeah. Okay, it's just only depend on the property of the medium, and for a wave on a string, the string is a medium. A sound wave is a wave of compressions and refractions of a medium such as air. Yeah. So we talk about this, and yeah, this like a sound like in this microwave vibrate and left and right, and then compress uh, the air in front of this one, and then it will like generate a sound wave, and this sound wave related to this property like the temperature, room temperature, and the mass. Yeah, like the air like mass. If this air is CO2, yeah, we have already talked about how to calculate it. It is O2, H2. Yeah, it's the same thing. And the other wave is electromagnetic waves. And these waves, such as light wave, you can see the light can be transferred can be travel uh, in a vacuum environment. Am I right? And also some like microwaves and the X-rays, radio waves, it can be transferred in a vacuum environment. Yeah. Okay. And they don't require a medium. All electromagnetic waves travel at the same speed in a vacuum, like this speed. Yeah, you can find these things in textbook P 400 and 41. And let's continue review. And we talk about the graphical description of waves. Actually, for the graphical description, we have two different graphic for to describe the waves. One is a snapshot graphic. A snapshot graphic is a picture of a wave at one instant in time for this is one snapshot graphic, which means when it is a fixed t in t0 t1, what's the wave looks like. Yeah, is for a periodic wave, the wavelength we call it, we define it lambda. Yeah, the wavelength we call it lambda. And the other like graphic we call it historiography. A historiography is a graphic of displacement of one point. It's just in one point, in a medium, like a versus time. For a periodic wave, the period t is the time between two different crests. Yeah, you can see this is a crest, this is another crest, and this is a period t. And this is historiography. It's just a one point, like how one point moves as the time pass. Does it make sense to you? Okay, this is like a graphical descriptions for a wave. And the other description, we call it a mathematical description of waves. And usually we can use mathematical form, mathematical we will use like a sinusoidal form to describe a sinusoidal waves. You can see many waves, they just their like a move form is just like a sinusoidal form. Yeah, so sinusoidal waves are produced by a source moving with simple harmonic motion. Yeah, if a source moving with simple harmonic motion, and then this wave we can use sinusoidal form to represent it. Otherwise, it cannot. Yeah. So the equation for a sinusoidal wave is a function of position and time. We talk about this. Why it's just like if we talk about the oh sorry. I don't know if you remember, like the t the displacement of wave according to we just write like this x no, t yeah, and if a displacement change according according a distance, and then we can use this equation. And this those two equations can be combined to this one. And why? I give you the reason. What if we write it like this? If the x is 0, it is just a constant. It's just exactly this thing. And it's if x 0, which means if t 0, I just left. Yeah, cosine 2 pi x. And we just combine them, and then we can use this one. Yeah, because you just change this part and this part. Yeah, here there is a positive and negative. The positive means the wave travels to left, and the negative means the waves travel to right. And we also explain that, yeah, for example, if I give you an example, for there is like a line, it is YKX, am I right? If it is travel to, if it is moved to left, to right, which means you need to use x minus 1, replace x, am I right? And if it is moved to right, to left, you need to we use x plus 1, like plus 1 to represent it. Yeah. Does it make sense to you? Yeah, it's a similar thing. And also for sinusoidal waves, we have like yeah, you can see for sinusoidal waves, the period and the like frequency is very important for sinusoidal waves. And based on the like frequency and all the period, we can like get the velocity for sinusoidal waves. Yeah, we talk about this next class. Yeah, this is the next class we have already talked about. In this class, firstly, we let us explore more about sound and light waves. Yeah, you can see. Firstly, let's talk about sound waves. And as you can hear this picture, yeah, we have already talked about it. Yeah, actually, the loudspeaker core, there is a core that you didn't see it, but there is a core. Like move back and forth, and creating like a regions of higher and lower pressure. Yeah, there is a pressure, compressions and rarefactions. Yeah, like as a core of loudspeaker moves forward, it moves air molecules closer together, creating a region of higher pressure. A half circle later, the core moves backward and the pressure decreases. Yeah, then it will like created the sound waves. Like if you just this is just have more like molo, molecules, and here is have less molecules like that. Yeah, the regions of the higher and lower pressures are called compressions and rarefactions, respectively. Yeah. Okay, does this make sense to you? Okay, this is some definitions. And the pressure waves of sound oscillate sinusoidally around the atmospheric pressure P atoms. Yeah, and when the wave reaches your ear, yeah, like here is the speaker, and this core like move forth and backward, move forward and backward, and then compression the air or the like rather affect the air and then form the wave. And when the wave reach here is your air, like when the wave reach your ear, the oscillating pressure causes your eardrum. Yeah, we talk about like your like structure of your ear, cause your eardrum to vibrate and then transferred to the cochlea. Yeah, where it is sensed. Yeah, then this then you can hear the sound. Yeah. And humans with normal hearing can detect a range of 20 hertz to 20,000 hertz. Yeah, like if you do some labs, if the sound wave like frequency lower than this one, it will you cannot hear that. If it is higher this one, yeah, it will be too much to your ears. Maybe it will hurt your ears. So just be careful about that. Yeah, this is some sound waves about. And let's talk about one example, range of the wavelength length of sound. Like what are the wavelengths of sound waves at the limits of human hearing and at the mid-range frequency of 500 hertz? Notes sound by human voice are near 500 hertz, as are noted played by striking keys near the center of piano keyboard. Yeah, let's talk about this problem. Yeah, this problem is just like talk about our human hearing, and the strategy is like we will solve for the wavelengths using the fundamental relationship here. Yeah, this is we have already talked about the velocity of wave, like the sound wave, is related to the lambda, the wavelengths, and the frequency. Which means if you want to calculate the wavelengths, then if you know the frequency, luckily it seems you know, and if you also know the velocity, luckily you also know. Yeah, because we talk about in the room temperature, the velocity of sound is just around this one. So let's yeah, let's talk about how to resolve this. Yeah, for the three waves, you can see here it's talk about the limits of human hearing, from 20 hertz to 20,000 hertz, and also it will ask you the mid range 500 hertz. So for those three wavelengths from mental relationships give you this. Am I right? So you know the frequency and you know the velocity. Yeah, you can easily get the wavelength, am I right? And when it is 20 hertz, the wavelength is 70 meter. And when it is 5 hertz, it is around 0.69. And when it is 20,000, it will around 1.7. Let's assess this problem, this example. And you can see the wavelength of 20 kilohertz note is only 1.7 centimeter. At the other extreme, a 20 hertz note has a huge wavelength of 70 meter. A wave moves forward one wavelength during a time interval of 1 parent, and a wave traveling at 343 meter per second can move 70 meter during the one per 20 seconds period of a 20 hertz note. Yeah, this is some knowledge that you can know. And yeah, you can see the deep low frequency um, sound. It can moves far, and the high frequency it moves low. Yeah. Okay, let's continue to explore the sound waves. Yeah, like I said, ultrasound waves, which means the frequency is very high. We cannot hear it usually. And yeah, those ultrasound waves are high frequency sounds above our range of hearing that are used by some animals for echolocation. You know, like the dolphins, yeah, they can use the ultrasound to communicate with each other and to detect the other fish's location. Yeah, and the resolution that can be detected by an optical instrument or your eyes is limited by the wavelength of the light. Acoustic imaging is the same. The higher the frequency, the fairer the detail. Yeah. And animals that use echolocation, such as bats and porpoises, produce and sense high frequency sound. Yeah, this is some of the ultrasound, ultrasound waves we need to know. Yeah, that the ultrasound wave, the resolution for the ultrasound look that can be detected by an optical instrument. Yeah, so yeah, this is something about the ultrasound. You just know it. Yeah, that's fine. Okay, let's talk about one example, like the ultrasonic frequencies in medicine area. Yeah, like this is a biology problem. Yeah, to make a sufficiently detailed ultrasound image of a fetus in its mother's uterus, a physician has decided that a wavelength of zero point 0.5 millimeter is needed. What frequency is required? Yeah, like this is just you can see he give you the wavelength of the wavelength, and he asks you what frequency. Yeah, we know like the frequency is decided by what the wavelength and what the velocity. Am I right? So like we need to remember that the speed of sound in tissue is different from the speed in air. Like, do you remember there is a table? Yeah, you can recall like there is a table. You can recall it in find it in last class slides. And the speed of the ultrasound in the body is given in the table like 50.1 as 1,540 meter per second. Yeah, we can use this one. And then we can use the fundamental relationship for sinusoidal waves to calculate. Yeah, we know uh, the original like equation is equal like lambda uh, divide t. Am I right? Yeah, so it is lambda f. So which means f equal what? F equal v divide uh, like lambda. Yeah. Okay. Yeah. Now we know the like velocity. Am I right? Like this is a fixed value, and then the lambda the question has given you, so we can like calculate the frequency 3.1 megahertz. This is a reasonable result. Clinical ultrasound uses frequencies in the range of 1 to 20 megahertz. Lower frequency have greater penetration, higher frequency, which means the shorter waves shows the finer detail. You can see if we use this like higher frequency like ultrasound wave, and you can see the baby's nose, eyes, mouth, even the finger. Yeah, is it like amazing? Am I right? So actually, yeah, the ultrasound, we cannot hear you, but if you explore for a long time in an ultrasound environment, it will like harm your body. So, but for a short time, that's fine. Yeah. So you can see some the ultrasound like equipment. Some usually put in like a room. This room is dark. This room is like a small. Yeah. Okay, let's continue. Okay, let's see light and other electromagnetic waves. Like we just talk about like the sound wave is just like mechanical waves. Yeah, like if it needs a medium to transfer. But the light is kind of like a electromagnetic wave. Yeah, and also other like microwave, like radio wave like that. We can talk about those here. Electromagnetic wave is the oscillation of electromagnetic field. Electromagnetic waves include visible light, like radio waves, microwaves, and ultraviolet light. All electromagnetic waves travel through a vacuum at the same speed, like this one. I think this number, you are familiar with this number. Yeah, if all the like electromagnetic waves, yeah, travel through a vacuum with this same like speed. Electromagnetic waves have extremely short wavelengths. In air, visible light has a wavelength of roughly 400 to 700 nanometer. Yeah, it's very, very small. Like, there is some like a research area called called nano area. Yeah, it's just a research on the nano thing. Yeah, the very, very tiny small thing. Yeah, okay. Uh, let's continue to talk about light and other electromagnetic waves. Each wavelength is perceived as a different color. Longer wavelengths, like 700 to sorry. Yeah, 700 to like 600 to 700 nanometer are seen as orange and red light, while shorter wavelengths like the 5 to 500 nanometer are seen as a violet and a blue light. You can see here. Yeah, this is a longer wavelength. This is a shorter wavelength, and those range we can see that, but other, yeah, we cannot. Yeah, the visible spectrum is a small slice. Yeah, you can see it's very small compared with the out of the much broader electromagnetic spectrum. Yeah, those part we can see that. Yeah, and but others we cannot. Yeah, so. If it is the range is between like 6 to 700 and it 700 nanometer, and we can see it is like an orange red light, and then it will like a blue violet light, like a color. Yeah. Okay, let's see another example, like finding the frequency of microwaves. Actually, you can see we just focus on like find the frequency, find the wavelength, and find the velocity. Yeah, just use this equation like V equal like lambda this wavelength divided T or like a multiple frequency. Yeah, just use this equation again and again. So just remember this one. And the wavelength of microwaves in a microwave oven is 12 centimeter. Yeah, this it has already give you the wavelength. Am I right? What is the frequency of waves? I think yeah, the same thing. The frequency is related to the wavelength of the fundamental relationship. This one, yeah, same thing. And the microwaves are electromagnetic waves, so their speed is the speed of light. Yeah, yeah, it's just like around, yeah, this one. So we know the velocity, we know the wavelength, so it's easy for us to get the frequency. All right, use this equation. Yeah, use this equation and V here, lambda here, then 2.5 gigahertz. Yeah, this is a high frequency, but the speed of the waves is also very high. So our result seems reasonable. Does that make sense to you? Okay. Let's see the other like example. The new generation of cordless phones use radio waves. Yeah, this is another kind of like a magnetic wave, radio waves. At the frequency of this one, what is the wavelength of these radio waves? Yeah, here let you to calculate the wavelength. Am I right? So like we still use like a V equal like a lambda frequency, and now like let's use like lambda equal what? V divided F, am I right? V equal what? We just know that if in the vacuum the speed is always this one, am I right? And then divide gigahertz. Yeah, you can like calculate. It is around 5.2 centimeter. Yeah. You can like calculate this again. Yeah. Any question, just let me know. I think this one is not difficult. Okay. Let's talk another thing. Energy and intensity. Yeah, intensity. A traveling wave transfers energy from one point to another. Yeah, just do you remember a traveling wave? Just transfer the energy, not transfer the material, not transfer, yeah, like it transfer the energy from one point to another. Like the power of the wave is the rate at which the wave transfers the energy and is measured in watts. Yeah, like yeah. To understand how to characterize the power of waves, like we must first understand how waves change as they spread out. Yeah, let's talk about how waves change as they spread out. Yeah, you can see here. There is a source. Yeah, a circular wave is a two-dimensional wave that spreads across a surface. Yeah, you can see, for example, the water wave. And if you put a like stone or a pebble into a pond, and then from this source, and it will have the it has a wave, and this circular wave is a two-dimensional wave that spread across the surface. Yeah. In a photography of ripple in a pond, like the location of the crests will be the wave front that are spaced one wavelength apart. Yeah, like from this crest to this crest. Yeah, it is waveless. Does it make sense to you? Yeah, we have already talked about this. And a circular wave. Uh, oh, sorry, I just put the same thing here. Okay, although although the wave fronts are circles, okay, you can see the wave front. This one is circles. The curvature isn't noticeable if you observe a small section of the wave front very far away from the source. Yeah, like if you observe this part, and you don't observe the whole, like just a range, this range. Yeah. Sorry. And then you can see it's not like a small section. It's just a line like that. It's not like it's appear to be a line straight. Am I right? Does it make sense to you? Yeah. It's not like a circle. Yeah, from this one, it's just if you observe in a very small like range, it's just like a straight. Does it make sense to you? Okay. Yeah, and uh this is for the wave spread in a surface. If spherical waves move in 3 dimensions, you can see some like for the light and the sound waves, they just the direction is everywhere. Like now it's just in a surface. It's in 3 dimensions, like the like a XYZ, like that. Yeah, you can see. Here is a sound, sound source. It's like this, and also this 3 dimension. Yeah, light and sound waves are spherical, like waves. The waves are 3 dimensional ripples, and the crests are spherical shells, still spaced one wavelength apart. Yeah, like from different direction. Yeah, it's just like spherical, like one wave apart like that. The wavefront diagrams are now circles that represent slices through the spherical shells locating the wave crests. Yeah, this is some some facts about the spherical waves. Yeah. Okay. Like when you observe a wave far from its source, like the small piece of a wavefront is a little patch of a large uh, sphere. The curvature of the sphere will be unnoticed, and the wavefront will appear to be a plane. You can see for the spherical wave, and you just like observe a small piece, and then you can see this is just like a plant. A plan wave describes observations of waves far from their source. The plans represent the crest of the spherical waves. Yeah, you can see this plan is just one crest, and this is another crest. This is the other, like the distance is just the wavelength. Does it make sense to you? This is some some definition, some facts for the spherical like a wave. Okay, let's continue. The intensity of light or sound, actually, the intensity of light is just like we in the real world we just call it like brightness or loudness. Like for the light, it's brightness, how bright this light, and how loud this sound. The intensity, yeah, just represent this kind of picture. Depends on the power of the source and the area that receives the power. Yeah, like this is the intensity, and this is the power of the source, and this is the like area that receives this power, and the like intensity unit are like W over square meter. Yeah, W means what watts, like how much power, and this is like a area. Like a wave focused on small area has a higher intensity than if it were spread out. You can see because from this equation, if the focus on small area, which means this one is small, so which means like it has a higher uh, intensity. Does it make sense to you? Okay, let's explore one example. The intensity of a laser beam, like a bright, like tightly focused laser point emits 1 m watt of light power into a beam that is 1 millimeter in diameter. What is the intensity of the laser beam? There, like we just use that equation, this equation. Yeah, this equation. And the light waves of the laser beam pass through a circle of diameter 1.0 millimeter, which means this is the circle area equation. Yeah, you should be familiar with this one because this is maybe you learn from in the high school. Yeah, the area of a circle is pi r square r. Like this is just half of no, this is just the diameter diameter, and this is just pi. Yeah, you can just write the put the number here, and then you can get the intensity. Yeah, this is the watt per square meter. Yeah, does this make sense to you? Yeah, let's assess this example. Like you can see, this intensity is roughly equal to the intensity of sunlight at moon on a summer day. Such a high intensity for a low power source may seem surprising, but the area is very small because the area is small, so the energy is packed into a tiny spot. You know that the light from a laser point won't burn you, won't burn you, but you don't want the beam to shine into your eye. So it is intensity similar to that of sunlight seems reasonable. Does it make sense to you? Yeah, because this laser point, yeah, is very like the area is the like area is very small. Yeah, and it actually it has the intensity is very big. Actually, it's just similar like the sunlight at noon. Yeah, so it's strong. It can burn. It cannot burn you because it's very small. But if it shine your eye, it will damage your eye. So be careful that. Be careful about that. Okay, does it make sense to you? Let's continue to talk about the uh, intensity. Like if a source of spherical waves radiates uniformly in all direction, then the surface area of the sphere is oh sorry, here I forgot 2 pi r square, because you can see here for a sphere. Yeah, here is a sphere. Yeah, it's like a for all the direction. It's a sphere. The area for a sphere is 4 pi r square. I think you know this. You have already learned this in high school. Am I right? So and the intensity is I equal P. Like this is the power from the source, and this is the sphere area. You can see here if the power is here, and this is the sphere. Actually, here just can only give you like a surface, but it's different direction. Yeah. Okay. The intensity ratio at 2 points is like this one. Yeah. Uh, like yeah, because you can see here, for example, here is I1, here is I2, and then I1 equal what? I1 equal P source 4 pi R1 like a square, and then I2 P source like a 4 pi R2 square. And then you can see you just remove this one, remove this one, remove this one, remove this one, and it will equal what? It will equal 1 over R1 square over 1 over 1 2 square. And then this is just this one, R2 square divided 1 R1 square. Yeah, does it make sense to you? Yeah, this is the intensity ratio at 2 points. Okay, let's check this example. Suppose you are powering a spacecraft with a 1.0 square meter array of solar cell with an efficient of 12%. Yeah. Above the Earth's atmosphere, where the intensity of sunlight is approximately this number. Yeah, actually, we talk about this number. Yeah, you can see in this example, yeah, the final result is 1,300. We talk about this is similar with the sunlight. Yeah, so here, sorry, here, the question is, what is the maximum power you could get from the solar cells? How much power could you get if your spacecraft was near Neptune, which is 30 times as far from the sun as the Earth? Okay, let's talk about this one. And let's write the equation here, and we know intensity equal what? Equal P divided area. Am I right? So here P equal what? Because the question let you get the maximum power. Yeah. So power equal what? Equal I multiple A. Am I right? This is area. Now I equal what? I equal 1,300. So. And what is the area? Well, area is like a, yeah, because this is a area. This is actually this is the area. Yeah. So one, this is the area, and but it with an efficiency of 12%. So you need to multiple this 12% because it's just 12% efficient, which means you can get divided point. Yeah, and this is 156 like a wall. And then how much power could you get if your spacecraft was near Neptune, which is 30 times as far from the sun as Earth? Actually, we know if it is far from the sun as Earth, here, in the Earth, the area is this one. Like we know this equation here, this equation. I'm sorry, this equation, I1, I I1, I2 equal R2 square and R1 square. Here, you can see the I1. We know it is 131, and how much power? Yeah, so it's a similar thing. Yeah, because the intensity and the power is the same thing. So like a P1, P2 also equal 2 and 2, 1. And then you can see here the area is 3 times far. So which means this this like should like a 3 square, like a P1, P2, R2, R2 square, R1 square. Yeah, and you can see the far, like the Neptune is 30 times as far from the sun, as the Earth. Here it is is R1, and it is 3 times far, which means the R2, this one is in the Earth, and this one is like is Neptune. So which means here it is 100, and this one we don't know, and this one actually it is 3 times R1. Am I right? So this is R1, which means like P2 equal what? P2 equal, this will be divided here. P2 equal 156 divide like 30 square. It's around 0.17. Yeah. Yeah, you can calculate by yourself. Actually, it's just like follow this equation, and follow it, because it's now a sphere. So it's follow this equation and follow, oh, sorry. Oh, follow follow this equation. Yeah, this equation. Yeah. Okay. Any question, just let me know. Okay, let's continue. Now let's talk about the lawlessness of sound. Generally, increasing the sound intensity by a factor of 10 results in an increase in perceived loudness by a factor of approximately 2. This is just a fact. Yeah, you just remember that general increase is the sound intensity by a factor of 10, resulting in a increase in perceived loudness by a factor of approximately 2. The loudness of sound is measured by a quantity called the sound intensity level. Yeah, I think maybe you guys have already heard about this before. The sound intensity level is measured on a logarithmic scale. Yeah, this is a mathematical term. I will talk about later. Because the perceived loudness is much less than the actual increase in intensity. Yeah, let's talk about why it's just like this. You can see. We will talk about one term called decibel scale. Like first, the threshold of hearing is the lowest intensity sound that can be heard. Yeah, we define this one is the lowest intensity sound that can be heard. It is where we place the 0 for our loudness scale. For the average human, it's so this is the lowest intensity sound we can hear. Yeah, it is about 1 multiple like this small thing watt per square meter. The sound intensity level is expressed in decibels, short by dB, as like yeah, this level can be impressed using this equation. Yeah, this is like sound intensity level, and it is 10 dB and log log base 10 1 over 1 0. 1 0 is the threshold of hearing, like it's the lowest intensity sound. Yeah, like sound intensity level in decibels for sound of intensity I. Yeah, you can, if this is the lowest one, and this is the intensity you can get, and then you can decide the sound intensity level. Yeah, does this like make sense to you? Okay, let's continue. As a reminder, like logarithms work like this. Yeah, this is a mathematical thing. If you press a number as a power of 10, and the logarithm is exponent, yeah, you can see here log base 10. This is tens like a power 3, and which equal what? Which equals 3. Yeah, this is the logarithm of this number is exponent. Yeah, do you remember that? Yeah, you can. I think you should learn this in high school or some like a basic like a college mathematics. Yeah, right at the threshold of hearing. Well, I equal I0. The sound at this level is you can see this is the lowest. Yeah, beta equal what 10 multiple 10 dB multiple. Yeah, if this one is the same thing, this will be 1. I'm right. 1 equal what? 1 equals 10 power 0. So which means this part will be 0. Does it make sense to you? So 0 multiple 10, it will be 0. 0 multiple 10, that will be 0. Does it make sense to you? Yeah. The threshold of hearing corresponds to 0 dB. This is what? Intensity level, which means the lowest is a 0. 0 level intensity level. Does it make sense to you? Yeah. Okay, let's continue. Yeah, we can find the intensity from the sound intensity level by taking the inverse of the log 10 function. We can recall like from the definition of the base 10, like rhythm that, yeah, we have already talked about that. Apply uh, apply this to the equation 50, this one 50 like 50.40, sorry, this one. Yeah, we will have this equation. We will have this equation. Yeah, so yeah, let me write it down and you will know that. Give me one moment. Okay. Yeah, we like the 50.14 is beta equal 10 dB, like a multiple log 10 base I divide I0. Am I right? So which means like it can be read like a beta divide 10 dB equal log base 10 I0, and which means like it will equal, if you want to remove this one, it will be like I divide I0 equal 10 power beta divide 10 dB. This is just the exponent. Yeah. And then I equal what? I equal I0 multiple this one. It's the same thing. Does it make sense to you? Yeah, you can like do this by yourself. Like a fairly short exposure to 120 dB can cause damage to the hair cells in the air. But lengthy exposed to the sound and at intensity levels over 85 dB can produce damage as well. So if you are in a like a noisy environment for a long time, it will damage your air, like the hair cells in your air. So be careful about that. Don't put yourself in a very noisy environment for a long time. Yeah. Okay, let's talk about there are some like sound intensity levels and intensities of common environment sound. You can see this is a threshold of hearing. Like if the intensity sound is this value, we call it 10 dB. We have 0 dB, and then the person breathing, it is just a 10 dB. It is a whisper, it is 20, and the classroom during test but no talking, it is 30, and the residential street, no traffic, it is 40. It's just like a midnight in the street like that. It's quiet restaurant, it's 15. and no more conversation existing, and busy traffic is 70, and vacuum cleaner is 18. You can see we just talk about like the 85 dB also can damage you as well. Here it's 80, so it's very close. Yeah, that's the reason why when the vacuum like cleaner opens, you will feel uncomfortable sometimes. Does it make sense to you? Yeah, and you can see if you are in the Niagara Falls, it is 40, it is 90. So what does this mean? This means if you go to the Niagara Falls, please don't be there for too long time. Am I right? Just maybe like less than half hour. Okay, does this make sense to you? Okay, this is like it's a this is Hammer 100 is a home stereo at maximum value. So don't make your home stereo too loud. It may hurt your ear your ear. Yeah, and rocket consent, and this is threshold of pain. Yeah, over like 130, and you will it will damage your ear. Absolutely. Yeah. Okay, let's continue. And this is like the summary results, like census 52. Like this is the summaries for power wave and intensity. Yeah, like we have different measurement of the energy carried by waves. You can see this is a intensity of a wave is a power per square meter of air. Air like this is intensity, this is a power, this is area that we have talked about a lot. Like from this equation, we can get the power can like equal the intensity multiple area. Yeah, and this is for like a surface like that, and this is a spherical wave spread over the surface of a sphere of increasing size. Like this is the source, and it will spread out, but in a but the this is 3D like a dimension. So like the power will the intensity equation is just like this. The I equal source power and divide like this is the surface of sphere 4 pi like r square. Does it make sense to you? Yeah, this is just the surface area of sphere of radius. Okay, this one. Yeah, this if you want to calculate this one, this is R. If you want to calculate this is R. Yeah, does it make sense to you? Okay, and then we define the sound intensity level. Yeah, intensity level, we just use this equation, and this is the threshold. Yeah, and this is like the phonon like intensity, and you can calculate the sound intensity level. And the smallest intensity human can sense is just this one. And we can also compute intensity from sound increase level. Yeah, use this equation. We have already talked about that. And you can find all these things in this page, textbook, like page 535. Okay. Okay, let's talk about the other one. The other example and finding the loudness of a shout. Yeah, you can see like a person shouting at the top of his lungs emits about 1.0 watts of energy as sound waves. What is the sound intensity level? 1.0 meter from such a person. Actually, I put a funny picture. Yeah, you know, like in our Chinese culture, there is a different kind of kung fu. Yeah, you know, like there is one kung fu. The name is Shi Hou Gong. The Chinese name is like a lion shouting, like tiger shouting, like a kung fu. Yeah, so like some people they can damage the enemy by shouting loudly. Yeah, interesting. Am I right? So, okay, let's back to this example. Okay, the strategy we will like assume that the shouting person emits a spherical like spherical like sound wave. Since that is this sorry. Yeah, this sentence is like 50.2. I gave the details for the decrease in intensity with distance and the calculation of the resulting sound intensity level. Okay, let's talk about the how to solve this. At the distance level 1.0 meter, which means R is 1. Am I right? So we use this equation. We use this equation and the like the power it has give you 1.0 watt power, and the like the distance is also 1, so the R is 1, and we just put the 1 here and 1 here, and then we can get the sound intensity is just this one. uh, yeah, and also we can use the sound intensity level and put it here, and then it is the intensity level. Yeah, put it here, and this is just the the threshold. And other we know that, and then it is 110 dB. It is huge. Am I right? Sometimes when people when people like shout loudly, and you will feel uncomfortable, especially someone have the kung fu. Yeah, just kidding. Okay. Okay, let's assess this question. It is quite loud, yeah, compared with the value in table 50.3, I'm right? It's almost here. Yes, sorry, almost here, I'm right? Yeah, amazing, these people. Okay, and like as you might expect. Okay, let's continue talk. Yeah, let's talk about some interesting. I think some students want to learn some like want to be a doctor later in the future. Maybe some student interested in the biology thing. Yeah, this one is like a kind of medical thing, biology thing. Yeah, hearing hears. Actually, this hearing hears. Yeah, it's interesting. Like you can find it in your air. Yeah, this electron microscope picture shows the hair cells in the culture of the air that are responsible for sensing sound. This is just like a sensor. Yeah, even very tiny vibration. You can see actually this one, I think it is soft. Yeah, even very tiny vibrations transmitted into the fluid of the culture, like they fly to the hairs, triggering a response in the cells, and the motion of the basilar membrane by as little as 0.5 nanometer, about 5 atomic diameter, can produce an electrical response in the higher cells. With this remarkable sensitivity, it is no wonder that loud sounds can damage these structures. Yeah, that's the reason why the loud sound can damage those structures. Am I right? Because it's so sensitive. Okay, let's continue. Let's talk about the other example. Yeah, you are doing a shop where the noise level is a constant uh, 90 dB. Yeah, it's not small. It's quite loud. And the question is your air drum has a diameter of approximately 80.5 millimeter. How much power is being received by one of your air drums? And the question B, this level of noise is damaging over a long time. So you use air plugs that are rated to reduce the sound intensity level by 26 dB, a typical rating. What is the power received by one air drum now? Okay, let's talk about yeah, I think this one is not like that difficult because we have already learned those equations. Yeah, you can use this power, this equation. P equal what? P equal I multiple A, am I right? So here you know the like also you can use this equation. Uh, yeah, this equation. Uh, yeah, this equation. This this equation. Yeah, and yeah, this equation. And now you know like the at noise level, the intensity level, noise intensity level, and then you know beta. Yeah, beta equal what? Let's write this it also down. And it 10 dB and log 10 I divide I0, and then yeah, this is we know the I0 and we know the beta. Yeah, it is 90. It is this one. You know it is equal this one. Yeah, one. Yeah, and then you can calculate the yeah, here they ask you like then you calculate the I, that's intensity of this sound, and then use this equation because you know the area, right? Then you can use this equation to calculate the power. Does it make sense to you? And the level of noise damage over so and yeah, reduce the level by, which means the sound intensity level will divide what is 6 4, and then you use the new value to use this equation and this equation to calculate this. Yeah, you can do this later. Okay, does it make sense to you? Okay, any question, just let me know. Okay, let's talk about some applications. The Doppler effect and shock waves. Actually, I think most students hear about like the Doppler effect. I'm right. And before we talk about this, I want you guys to uh, see a video with me for a moment. Okay, let's see. Yeah, this is a typical Doppler effect. And like after watch this video, I think maybe you have some ideas about Doppler effect. Yeah, it is a change in frequency due to the motion of the source or observers. Observers, you can see when the people in the car and it blow the tramp and uh, the sound is the same for the people who blow it. Am I right? But when like the for the people observe that sound, and when the car is close and it the frequency seems high, and then when it like left, the frequency will like become slow. Am I right? Become lower. Yeah. So this is we call it Doppler effect. Yeah. This effect yeah, this effect is heard as a higher pitch of an ambulance siren as it approaches you and drops after it has passed by you. Actually, we will have a lab about this. Okay, a shock wave is produced when an object moves an object moves faster than the sound of speed. We sometimes we call it like ultrasound, like uh, things like ultrasound plan. Yeah, so we will talk about this one. And when you heard the cracking of the whip and the tip of a whip is moving at, oh, sorry, I talk it wrong. It is supersonic. Yeah, supersonic speeds. Yeah. Okay. Let's continue. Sound waves from a moving source. Yeah, why? Like, let's explain why this Doppler effect. You can see a source of sound waves is moving away from this. There is a people who called Pablo, and there is another one called Nancy. This is the south nerve sound, and this south nerve sound is moving away because of the direction here. So it moving away from Pablo and towards Nancy with the speed of Vs, and the subscript on Vs, like here, means it is the velocity of the source, not the speed of the waves. Yeah, this is velocity source, not the speed of waves. And the source emits a frequency of Fs as it travels. After a wave crest leaves the source, its motion is governed by the property of the medium. The motion of the source has no effect on each crest once emitted. Actually, this we have already talked about the waves after the wave leaves the source and it's not related to the source. It's just depend on the medium. Does it make sense to you? Yeah, we have to talk about this, and you can see here is the source, and this source will move towards to Nancy, and yeah, each circular wave front is centered on where it was emitted. Yeah, for example, this one is for the source 0. This one is for the source 1. This one is source 2. This one and source 3 didn't show it. Yeah, okay. Due to the motion of the source, the wave crests bunch up in the direction of motion of the source and are stretched behind it. Yeah, the wave crest, you can see this is the wave crest. Bunch up in the direction of the motion of the source and are stretched. You can see this is close. This one, yeah, it is close, yeah, but this is stretch, yeah. The wavelength is the distance between crests, yeah, here, which means this is a wavelength and this is a wavelength, and yeah, it's wavelength. Uh, Nancy mirrors, yeah, if this is Nancy. Nancy mirrors wavelength that is less than the wavelength if the source were stationary. Yeah, if the source is we call it we set it like maybe lambda initial. Yeah, the Nancy mirrors the wavelength it will be like less than the wavelength if the source were stationary. And the lambda 0 equal like v over fs. This is the equation we have already know, where v is the velocity of the wave and lambda 0. Yeah, here is lambda 0 is a wavelength observed by Nancy. So like the wavelength Nancy observed, it will less than the wavelength, like the original wavelength. And similar, the wavelength is larger behind the source. This is behind the source, which means the Pablo will observe the wavelength larger, bigger than the wavelength, the original, if the source were stationary. Does it make sense to you? Okay. Let's talk about that. Yeah, the frequency F plus, you can see here, the Nancy detects the frequency F like a plus, and the Pablo detects the frequency F minus. Yeah, suppose this is for Nancy, this is for Pablo, and the frequency F plus equal what? Equal V divided lambda plus. Actually, this is okay. Yeah, sorry. Yeah, I think this stationary, this is the original wavelength. Yeah, if the source were stationary and the lambda 0 is equal this one, the fs is the original frequency, and the I think there will be a lambda plus. Yeah, is the wavelength observed by here. Lambda plus is observed by Nancy, and lambda negative minus is like a wavelength observed by like Pablo. I think I just write here a little mess up. Yeah, just remember lambda 0 is the original like wavelength, and lambda plus is Nancy detect, and lambda minus is Pablo detect. I think this is easy to understand. So for the frequency, this is Nancy observe the frequency. F plus equal V divided lambda plus. Lambda plus is Nancy detected the wavelength, yeah, detected by the observer who the source is approaching is higher than the frequency emitted by the source. The observer behind the source, like the Pablo, detects the lower frequency f minus than the source emits. Yeah, the Doppler effect is a change in frequency when a source moves relative to an observer. You can see this is for the Nancy, like if the observer is like a front to the source. Yeah. Okay, and this is the frequency of the source, and this is the speed of source, and this is the speed of wave. Yeah. So this is how to calculate the frequency. Like the similar thing, if someone receding source, and this the frequency will just equation is just like it just replace minus with plus. Yeah, does it make sense to you? Because you can see this one will be smaller frequency, so this one will be higher. Yeah, does it make sense to you? Okay. Let's talk one question, like quick chat one question. Yeah, a siren like a siren emits a sound wave with frequency f0. The graphic shows the frequency you hear as you stand at rest x equal 0 on the x-axis, which is the correct description of the siren's motion. You can see. At the beginning, this you can see here it is a time. So at the beginning, this is f now is the source frequency, which means at the beginning, like your frequency is f negative, am I right? And after 2, and your like frequency is like a and minus like a positive, like a plus, am I right? So which means this source at time 0 to 2, it is move away, yeah, from you, and then close to you and pass you, and then close to you and get to the F and move forward to you, but it doesn't reach you because the frequency is now like a f0. It's just more than f0. Does it make sense to you? So which one is right? This one, am I right? It moves away, yeah, because at the beginning it is f like a minus, f like negative, and it is move away you for 2 seconds, then inverse direction at t, inverse direction, and move forward to you. Yeah, am I right? And but it doesn't reach to you. If it is reach to you, and the frequency will become f naught. Does it make sense to you? Yeah. Okay. Any questions? Let me know. Yeah. This is a Doppler shift to lower frequency means it's moving away. Yeah. Does it make sense to you? Okay. Let's continue. Let's see the other example. How fast are the police driving? Police siren has a frequency of 550 hertz as a police car approaches you, like 550 hertz after it has passed you and is moving away. Like how fast are the police traveling? Like here, how fast, which means it let you to calculate the velocity, am I right? Yeah, let's check the strategy. The siren's frequency is altered by the Doppler effect. The frequency is f positive as like f plus f positive is the same thing as the car approaches, and f negative as it moves away. We write two equations for this frequency and solve for the speed of the police car, like yeah, speed, and we use those two equations. Yeah, those two equations. Okay, let's write it down here. This one and this one, and you can see like because our goal is to find the VS, so let's just rewrite the equation. Subtracting the second equation from the first one. Yeah, you can see like let's maybe you may think the equation 50.16 is not like this. Yeah, because it change a little bit. Yeah, because the original is F. Sorry, is F minus equal Fs 1 and F positive equal Fs 1 minus VSV. Yeah, so we can, from this one, you get this one, from this one, you get this one. And you can see this one, Fs equal this one, Fs equal this one, which means this part equal this part. Does it make sense to you? Yeah, and then we like let 1 VSV F negative equal 1 VS 1 F, and then you can get this equation from this equation. Yeah, you can see F VSV F equal F plus minus VSV F. Yeah, and then you just put it here, F minus minus F positive, negative, positive, and then plus F negative minus S positive VSV. Yeah, doesn't make sense to you. Is this equation equal 0? And yeah, and then from this equation we can get the VS. Yeah, because we have already know the frequency F minus and F like positive. Yeah, which one is 550, one is 450. Yeah, and then you just put F positive, F negative to these equations, and then you can get the here V is just the like sound speed. Okay, and then we can get the like a velocity car speed. It is 34 meter per second, and actually we can translate to like a mile, and you will know it is around 75 mile, like per second, like that. But it is pretty fast, am I right? But it's reasonable for police car speeding with the siren on. That makes sense to you? Okay, let's talk about stationary source and a moving observer. And you can see here, the frequency heard by a moving observer depends on whether the observer is approaching or receding from the source. Actually, just now we talk about the observer is still and stand there, don't move, and the source is moving. And here we talk about the source is a stationary source, and the observer is moving. Yeah, actually you can see like it's a similar thing. Yeah, the frequency heard by a moving observer depends on whether the observer is approaching or receding from the source. It's just opposite from that one. If the observer is approaching, which means like the speed the observer the observer frequency will be increased. Yeah, does it make sense to you? Because you can see the frequency and for if it is receding from the source, and it will mean the observer frequency will decrease. Yeah, does it make sense to you? Okay, it's similar thing. Yeah, we can compare that one is this one. Yeah, this way is approaching source and receding source. Yeah, like approaching source, which means the source is close to people, observer, receding is it is like a like a get away from the source, and this one is just like the uh, opposite. Yeah, and if like the observer is approaching, which means like the frequency will equal this one and equal and this one. Yeah, and if the observer receding, yeah, approach, yeah, from receding from the source, and this is like the frequency will be decrease. Yeah, does it make sense to you? Okay, let's talk about the Doppler effect for light waves. Yeah, if the source of light is receding from you, the wavelength you detect is longer than that emitted by the source. The light is shifted towards the right end of the visible spectrum. That effect, we call it redshift, and the light you detect from source moving toward you is blue shift to shorter wavelengths. Let's check this one. Okay, this one. Yeah, you can see if like the light like a receding you, and the wavelength will become like longer, and which means it will shift to this direction. Yeah, am I right? This direction, and then it will shift to the right part, right area. And if it is like approaching you, and then it will like shorter, it will shift to the blue area. So yeah, this is why. Does it make sense to you? Sorry. Yeah. Okay. Like all distant galaxies are redshifted. So all galaxies are moving away from us. Yeah, extrapolating backward brings us to a time where all matter in the universe began rushing out of a primordial fireball in an event known as a Big Bang. Yeah, I think everyone heard about that. Like all distance galaxies like are redshifted. Yeah, which means our galaxies are moving away from us continually. And at the beginning, it is just a small part, and then it move away far from us. Yeah, we call it like a Big Bang. Yeah, measurements show the universe began like a 14 billion years ago. Amazing, am I right? Like at the beginning, it's just a small point, and then expand, and then get away from us. Yeah, get away from. Sorry. Yeah, yeah, get away from us and expanded a lot bigger, and now form the universe. Yeah, now does it make sense? Yeah, is it amazing? Okay, let's continue. Yeah, frequency shift on reflection from a movie object. Yeah, a wave striking a barrier or obstacle can reflect and travel back to the sound. For sound, there is an like this is an echo. Yeah, you can. I think this one like you can easily to observe. Some like I don't know if you guys like hiking. When you go to a mountain to hiking and you you like shot to a mountain, and then your sound wave like strike the like a mountain, and then it will reflect, and then you can hear the echo. Yeah, so this is a typical example. Like for an object moving toward a source, it will detect a frequency Doppler shifted to a higher frequency. The time between the emission of a pulse and its return gives an object's position. Yeah, actually, yeah, there will be a lab for this, and the change in frequency of the returned pulse gives the object the speed. Actually, you can see this one and this one. Yeah, many like animals in the real world use the for example the bat and the like some other like animals, they just emit like echo sound echo, and then they use this like a they use the optical echo give them the object's position and the object's speed. Does it make sense to you? Yeah. Okay. Let's continue to talk about this. Like the echo from a moving object is a double Doppler shifted because you can see, yeah, there are two objects. Yeah, two, yeah, A object, one B object, and this A object is moving, and he emit some sound wave or light wave, sound wave, and if and B is also moving, it is not still, it's also moving. So when the A the sound wave meet B and then come back, and this A will know B's position and the speed like that. Yeah. So the frequency shift of reflected wave is just this equation. Yeah, this one is a shift in frequency on reflection. And this one, if the object is moving away, the frequency is decreased. And if the object is moving closer, the frequency is increased. That's red. Here is a positive and negative. Yeah, when the object is moving away, it will decrease. Yeah, it will be negative. And when it moving closer, and the frequency will increase like that. And this is the frequency of the source. Yeah. For example, A is the source. This is the frequency of A, and V now, the VO, the spin of the object. Yeah, this is B, is object, and V is the spin of the waves. Like this is the sound wave, the spin of the sound wave like that. Okay. The change in frequency of the returned pulse gives the object speed. Yeah, like you can see, if you want to get the object speed, yeah, sometimes the bat want to get the other bat speed or some object, the other object speed, and they just use his ecosystem to detect you can use this equation to calculate that. Yeah, okay, you can see for the V object, it will equal frequency shift in frequency on reflection divided to plus and divide Fs and multiple V. V is the spin of waves. Yeah, does it make sense to you? Yeah, we can get the object speed according from based on this equation. Okay, let's see explore one example the Doppler blood flow meter. Yeah, if an ultrasound source is pressed against the skin, the sound waves reflect off tissues in the body. Some of the sound waves reflect from blood cells moving through arteries toward or away from the source, producing a frequency shift in the reflected wave. A biomedical energy is designed a Doppler flow meter to measure blood flow in an artery where a typical flow speed is known to be 0.60 meter per second. What ultrasound frequency should he use to produce a frequency shift of 1,500 hertz when this flow is detected? So here, the question just asks you what ultrasound frequency used to produce a frequency shift of 1,500. Yeah, so the strategy is the ultrasound is reflected from a moving object like the blood is moving, am I right? So we just use this equation 58. Yeah, this one. This one is 58, and then we just write it down. Yeah. Okay, in equation 50.8, V now, the V0 is the spin of the blood. Yeah, we know that the spin of blood is what is, yeah, you can see where a typical flow speed is known is this one. Okay, 0.6. the speed of the sound in human tissue and is this one we have already talked about this before. Yeah, also you have checked in that box, like you can find it in the textbook. Yeah, we can rewrite equation 55 to calculate the frequency of the emitter. Yeah, you can see here. Actually, we know the frequency of shift. I'm right. Yeah, we know the equation is just like this frequency shift. Oh, sorry. Yeah, frequency shift equal what? To F S. This is frequency source, and like V object and V wave. Am I right? So like here we just rewrite it like because we want to find the source like frequency. We have already know the shift reflect frequency. Yeah. So like the F S equal what? Equal delta F divided 2 and also multiple because you need to move this one to this direction, so it will be flip. V divided V object. This is blood. Am I right? So it's just this equation. And here we know the V like wave. It is this one. This is a sound like a travel. The speed sound travel in like a human tassel. And this is the like shift frequency, shift flat frequency. And this is a blood shift speed, blood like speed. So we can find the like a source speed. It is 1.9 megahertz. Yeah. Okay, like let's assess that. And Doppler units to measure blood flow in deeper tissues all actually work at around 2 megahertz. So our answer is reasonable. Yeah. So you can see here is a picture for that. There is the transducer will like it will emit like a frequency, and this frequency like we for this equation for this question it is around 1.9 megahertz. Yeah. And then this is a blood is flowing, and then here is like a this is this is a Doppler shift frequency. It is five 1,500. Yeah. And the velocity like for the wave in the like Tesla is like this one. And the we know the speed for the like wave sound wave in human Tesla, and we also know the speed for the blood flow, so we can calculate the frequency like for this one. Does it make sense to you? Yeah. Also, yeah. Okay. Let's talk about the shock waves. Yeah, this is another interesting like phenomenon. Yeah, a shock wave is produced when a source moves faster than the waves, which causes waves to overlap. You can see some like a super sound, like a super sound plan. Yeah, you can see here like the source the wave is moving. Yeah, the source, this is the source of wave is moving to the right at the VS. The position at times is T0, this is 0, this is T, this is 2T. Like at each point, the source emits a wave that spreads out. A snapshot is taken at a T equal like a like a T, 7T. Okay, you can see quest 3 was emitted at the T equals 3T, am I right? 4T is just like you can see before the snapped. The wavefront is a circle of radium 4 lambda. Am I right? Yeah, this is like a 3, and this is 4, and you can see 4 is in 3's area. Am I right? Circle, yeah. So the sound speed is greater than the wave speed. So during time t equal t40, since crest 3 was emitted, the source has removed further than crest 3. Yeah. Okay, the overlap waves add up to a large amplitude wave, which is a shock wave. Yeah, does this make sense to you? Yeah, you can see here, the source uh, moves to this direction, and when it is here and it emitted it here it emitted this and it here emit this one and emit here emit this one, and you can see when the before emit that here, and the speed and the this object has moved faster than this one. Yeah, so it already passed it as a the sound speed there, speed there. So this is we call it shock move. You can see there are some example. Sometimes when you see the plane in the air, this is a supersonic situation phenomenon. Yeah, this is a supersonic phenomenon in the water. Like this ship, the speed is very fast, and which is faster than the south move. Yeah. A source is supersonic if it travels faster than the speed of sound. A shock wave travels with the sound with the source if the supersonic source passes an observer. The shock wave produces a sonic boom. Yeah, this is we call it a sonic boom. Does it make sense to you? Less extreme examples of shock waves include the weakening of a boat and the cracking of a whip. Yeah. Okay. Okay, yeah, this is what we learned in this chapter. Yeah, in this chapter, let's do a summary. And in the chapter 50, we talk about some we learn about the wave model, traveling wave, and sound wave, light wave, and some applications, like how to describe the traveling wave. Yeah, this is what we focus on chapter 50. And let's review one by one. Firstly, we talk about some general principles. What is a wave model? Actually, we talk about the wave model is based on the idea of a traveling wave, which is an organized disturbance traveling at a well-defined wave speed v. Yeah, there are two different kind of traveling waves. One is transverse waves. The other is longitudinal waves. And transverse waves is just the particle of the medium move. This is a particle of medium move direction is up down. But the wave moves towards to this direction, and this direction and this direction is perpendicular to each other. So we call this is a transverse wave. And the other wave we call the longitudinal waves, which means the particle of the medium they just moves left and right, left and right, and also the waves travels towards this direction. Yeah, this direction and this direction is just a parallel. Yeah, so this kind of waves we call it longitudinal wave. Okay, and we know a wave just transfer energy. There is no material or substance transferred. Yeah, otherwise it would be it would be yeah, you must be, if you can do this, you must be the Jesus, because you can now make a one to make water to one. Am I right? Become okay. Yeah. Okay. Let's. So for the wave model, there are usually there are two different kind of waves. Mechanical waves usually require a material medium, such as water wave, the sound wave. Yeah, and also strain wave like that. The speed of wave is a property of a medium, not the wave. So you can see for the strain, it's just related to the strain's property, like the tension and the like a linear intensity. And for the and it's not dependent on the size and shape of the wave. And for a wave on strain, the strain is a medium, and a sound wave is a wave of compressions and rarefactions of medium, such as air. Yeah, if it is in the air environment, and the velocity is related to the room temperature and the mass of like a molecular, like for example in the air like that. And usually the sound speed in like air, we know it is 375 or 76 like that. Yeah. Okay. And there is another like waves, we call it electromagnetic waves, and those waves they don't require a medium, and those waves such as a light wave, yeah, light can be like a travel in a vacuum. Am I right? And also the microwave, some radio wave, and in all electromagnetic wave travels at the same speed in vacuum. Yeah, this one. Usually when we do a calculation, we also use this one in the air, in our air environment. It is close. Yeah. Okay. Mm. And let's talk about the like some important concepts. Yeah, and usually we want to describe the waves. There are two different kinds of this description form. One is a graphical representation of waves. For the graphical representation waves, we have two different graphic, and one is snapshot graphic. It is just for one specific time. What is a wave like doing? And yeah, it is a picture of wave at one instant in time. For a period wave, is a for a periodic wave, the wavelength is lambda. You can see this is a wave move, and this is just a wavelength lambda. And also we can use history graphic. Is a graphic of displacement of one point. You can see in this wave moment, we just choose one point. And this one point, as the time pass, what this one point moves. Yeah, this we call it history graphic. And because like it's like related to the time, so you can see it's uh, for periodic wave, the periodic t is the time between crests. This is the wavelength is the displace is the distance like between two crests. Yeah, does it make sense to you? So we have two different graphics to represent a wave, and this is the graphical representation of waves, and the other is the mathematical representation of waves. And you can see if a source moving with a simple harmonic motion, we can use sinusoidal form to represent this wave. And then we have this equation. Yeah, like this plus, this positive, negative, like a plus, minus. The plus means wave travels to left, and like a minus, which means the wave travels to the right. I have already explained that. Yeah, like for sinusoidal wave, and we also can we know like the t period and the frequency is very important because we can use frequency and wavelengths to calculate the velocity. Yeah, also you can see and lambda t. Yeah, you can also use this equation. Yeah. Okay, let's continue. And yeah, then we talk about the intensity of a wave of a wave. And for the intensity of a wave is a ratio of the power to the area. Mm, you can see like this is the intensity of a wave, and this is the power, and this is the area. And for spherical wave, the power decreases with the surface area of the spherical like a move fronts. Yeah, because you can see this is the equation should become 4 pi r square. This is sphere surface. Yeah, does it make sense to you? Okay, we have already talked about it. And okay, the loudness of a sound is given by the sound intensity level. This is a logarithmic function of intensity and is in units of decibels, dB. Yeah, we short for dB. Okay, the sound intensity level in dB is given by this equation. Yeah, this is the threshold. Yeah, I0 is this value. The threshold of hearing, the quietest sound that we can hear. A sound at the threshold of hearing corresponds to 0. Yeah, we just defined it 0. Yeah, because if you put I0 here, and you can see the beta will be 0. Okay, does this make sense to you? Okay. And then we talk about the Doppler effect. A Doppler effect is a shift in frequency when there is a relative motion of a wave source and frequency fs with speed v and observe. A moving source for a moving source like a stationary observer and if like you have a receding source and then the frequency like you can get from this equation. If you have if you approaching source and then you will have a frequency this one. Yeah, and then if the observer is moving and the source is stationary, and then approaching the source and your frequency will become this one. And if moving away from the source, and your frequency will become this one. And a reflection from a moving object, like if like a V naught much smaller than V, you can use this equation. Yeah, when an object moves faster than the wave speed in medium, and a shock wave is formed. Yeah. Okay, this is what we learned for this chapter. Okay. Yeah, so many things, am I right? But what do you just remember for today's class? And for next class, you just you, like try to know how to calculate different for to calculate velocity in different situation in different medium, the wave velocity and for sonar wave how to calculate the like velocity. And for today's class, and you just focus on how to like calculate the intensity and how to calculate the intensity level and how like if the if you have there is a moving source and a stationary observer, how to calculate the frequency. If there is a moving observer, stationary source, how to calculate the frequency. Yeah, it's always related to a frequency and a period thing like that. And yeah, there are some applications, Doppler effect, shockwave. Yeah, you just need to be familiar with that. Okay, this is today's class. Thank you. Any question, just let me know. Okay, remember, remember just, let me show you. Okay, oh no, this one. Okay, this one. Just remember, I will give you a link. I will, class. Sorry. Oh yeah, I will sorry, I just, oh my God. Yeah, I will give you this link, copy link to join. And I will email to you. I'll give you an announcement, and you will no this link, and you will through this link to join this class. And remember, you don't need to pay the rejection lessons. You don't need to pay the lessons. We have already paid it for you, so you just need to enroll this class, and then you will have the second lab. Okay, any question, just let me know. Okay, thank you guys, and hope you have a good weekend. Any questions, just email me, text me, let me know. Okay, thank you. Bye.